So we have finally come to this section where we are going to discuss about functions. I have already drawn these examples of relations from the previous section because we are going to use these examples. Actually, this is example 7 and this one is example 8, but because we are not following any number of these examples, so I just show the arrow diagrams of these relations. Let us now start with the definition of functions. Even before we see the actual definition, we know at least something about functions from the previous video. Recall that we already have said that functions are going to be nothing but relations, but some special type of relations. So this is what functions are. A relation if from a set A to a set B is called a function if every element of A has one and only one image in B under the relation F. We have to first understand what this thing is. So, as we said before, a function is nothing but a relation. A relation we know is is an object that links elements of one set to elements of another set. So we take a relation F from set A to set B, whose arrow diagram will look something like this. But now the extra condition for it to be a function is that every element of A of the first set must have one and only one image in B under this relation F. If this happens, then we will say that the relation F is a function. Now we know from our study of relations that if F is a relation from A to B, F is actually nothing but a subset of the Cartesian product A times B. As such, the elements in F look like this: ordered pairs of elements where the first component comes from A and the second component comes from B. And we also know that when such an ordered pair belongs to F, then we say that B is an image, not the image but an image of A under F. So what this condition is saying is that every element of A has one and only one image in B under F. Now what does this condition mean? Is this condition being satisfied in these examples? No. Let us first see this one. Note this word, okay. Every element of A has one and only one image. That means every element of A needs to have an image. That's not the case here. This element 6 does not have any image under that relation, this F. So this relation is not a function. The second example also shows a relation which is also not a function. So now we go to the other requirement of this condition, the other part of this condition, if you want to say it like that. Every element needs to have an image, but only one image, not more than one image. That has been violated here. All the elements of A have images. No element is sitting idle, like here 6 is sitting, which does not have any image under this relation, that relation. But the elements do not have unique image. There is more than one image for each element of A. So this is also not a function, but because of a different reason. Uniqueness of image is not present here. Okay, so that is the requirement. Now, it may be a little difficult to remember this condition at first when you see this. Okay, when you see it for the first time, it becomes a little difficult to remember. You may put so much emphasis on ascertaining that you need a unique image that you may forget the full condition. You may forget this every part, that every element of A first of all needs to have an image, and then that image needs to be unique for every element separately. Now, is there any way that we can remember this condition somewhat more easily than just simply say memorizing this sentence? Never do such things, okay? Because you may not really remember it when you need it, say in writing your exam or somewhere else. But always try to remember this kind of things by drawing some type of analogy with something from the real life. Let me just take this type of analogy. Say, what you are looking at, these arrow diagrams. Say these arrow diagrams represent some kind of shooting game where there are two teams of soldiers, snipers, whatever they are, whatever you can imagine them to be. The game is that each team gets a chance. When a team gets a chance, say team A gets a chance to shoot at the members of team B. The rule for a function is that each member has to shoot. No one can sit idle and relax like this. That is not allowed. And each soldier or each sniper, of course, can shoot at only one target, not more than one. So that condition should also be there. I mean, if you think of this relation from that game perspective, then here the snipers are using some kind of extremely advanced weapon which can shoot at more than one target at once. That is not allowed. We have ordinary snipers, good snipers, so that they do not just simply sit idly like this, and also, of course, at one time they shoot only one person of the other team, of the opponent team. After they get the chance to shoot these people, then in the next step, whoever survives, they get the chance to shoot back. So it's kind of a game like that. So that way you can remember. Each soldier has to shoot, and each soldier, of course, can shoot only one target at a time. If you can remember this, then you will never forget this condition and what relations are functions. Now we are going to state this same thing in a slightly different manner, or that's what they did in the text. So let us next see, in other words. So these are non-examples. These are not examples of functions. We will see examples, but let us now see the reformulation of the definition. In other words, if f is a function from a non-empty set A to a non-empty set B, you may have noticed one thing already. In the original definition, we did not explicitly say that A should be non-empty, B should be non-empty. But do not forget that in our original definition of a relation itself, we need the sets non-empty. Okay, so there is no need to separately say that the sets are non-empty once you mention the word relation. Here, however, just to remind us that we have non-empty sets, so the authors have written non-empty set A, non-empty set B. In other words, if f is a function from a non-empty set A to a non-empty set B, then the domain of f as a relation, f will have a domain, is A. The domain needs to be A because what is the domain here? Here the domain is A from which 6 has been removed. We know in general that the domain of a relation is a subset of the first set. That should not be the case. In case of a function, the domain has to be equal to A because the arrows should go out from all the elements. That's why we say that then the domain of f is A and no two distinct elements of f should or instead of using should, let me just write directly, assertively. No two elements, distinct elements of f have the same first element. The domain needs to be A. In this case, the domain is not A, so this is not a function. So in the hope of getting an example of a function, say one looks at this example instead. We of course already know this one is also not a function, but let's just go ahead systematically. First we check whether the relation here has domain A. Yes, it has. The arrows are going out from all the elements. Fine. Next, no two distinct elements of f have the same first element. If you look a bit carefully, this function, if you write this function out as a set of ordered pairs, because after all it's a relation, in that set you will have these two elements, say 9, 3 and 9, -3. We haven't given any name to this, say let me call it G. Say this relation is G. Then these elements belong to G. What is the requirement here? No two distinct elements of the function have the same first element. Here, however, for G, we are looking at two distinct elements. 9, 3 is one element, 9, -3 is another element. Such elements should not exist because although these are distinct elements, but they have the same first element, 9. That should not be the case because this happens precisely when more than one arrow goes out from a single element. So that single element appears as the first element in more than one distinct elements in whatever relation you are considering. If you have more arrows coming out of 9, you will have more such elements, all of whose first elements are equal to 9. That should not be the case. So this is another way of saying that the relation f is a function, although slightly more complicated than the original definition. You do not have to worry about these things too much. You just remember that shooting game. Each soldier has to shoot, and each soldier shoots only one target at a time. That's it. Then it's a function. Okay, now next come to the question of notation. Because we have already seen whatever we had to see about these two examples, I can now use this part. So such special types of relations are called functions. Now there are some symbols that will indicate some things. We cannot be expected to write everything in words and sentences. We need mathematical symbols. When f is a function from A to B, where of course it's understood that A and B are both non-empty sets. Okay. When f is a function from A to B and this ordered pair belongs to F, we write B equal to f of A. This equation and this relation mean exactly the same thing. Both of them mean that B is the image of A under F. Both these notations mean that B is the image of A under F. Look at the article, definite article B. Normally when such an ordered pair belongs to F, where F is a relation, we say that B is an image, okay, under the relation of A. However, because now this is not any relation but a function, so for a given A, that B needs to be unique. And this uniqueness of course is coming from that second part of our condition, that each arrow, or rather each soldier A is attacking only one soldier B of the opponent team. And that is why each soldier A has a unique target B. Each element A has a unique image B. The notation B equal to f of A is read as B is equal to f of A. Okay, that's how you read it. When you see this equation, that's how you read it. B is equal to f of A, or B equals f of A. In this case, A is called, of course, we already knew even while studying functions, there itself we defined what it means for B to be an image of A. Now the image is unique, so that's the new part, that's the new thing. However, when you have this relation between B and A, then A also gets a name in relation to B. A is called a pre-image of B. Note that we have B here, the image of A, but a pre-image of B. This indicates that maybe a single soldier B on the team which is being attacked, maybe he is being attacked by multiple soldiers from the attacking team. That is allowed. A single soldier cannot attack at the same time more than one soldier, but multiple soldiers can attack the same soldier of the team that is being attacked, where B is one member. Maybe B is a general or B is someone very important, that his death is really very important. So multiple soldiers are attacking B at the same time. We are going to see these examples, okay? And in fact, the text doesn't immediately offer us these examples, but I am going to show some such examples. Let's just see the examples now itself. But before we see the examples though, there is something else that I need to say here. When f is a function from A to B, there is a notation to express just this itself, that f is a function from A to B. We express this by writing a symbol like this, F followed by a colon, then you write A, then an arrow like this, and then B. Instead of saying instead of writing every time that f is a function from A to B, you write this. That means the same thing. Okay, so this is the symbol for that sentence. Alright, let me now create a relation which is a function in which that thing happens, that multiple people are attacking the same person. Without being too specific, I am just going to draw an arrow diagram like this. Oh, if I take just an abstract arrow diagram, you may feel that you are being cheated. So instead, let me just take actual sets. Say A is the set consisting of -1, 0 and 1, and say B is the set consisting of 0, 1 and 2. Okay, so simultaneously I am going to show something which is true in any function and which may cause confusion. So we have the three elements here, -1, 0, 1, and again three elements here, say 0, 1 and 2, and the relation that I am going to use to link these elements of A with the elements of B, let me write the relation there. say this relation is F and F consists of ordered pairs x comma y, of course, coming from A times B, such that y is equal to x square. If instead of writing F in the state builder form like this, if I write it in row star form, so that before seeing this, let's just see it as a state. What is it that we will get? The elements of A have to be taken -1, 0, 1. And the second coordinate of each such pair in F will be the square of the first coordinate. So if my first coordinate or first component is -1, then its square is 1, because y should be x square. When it is 0, 0 square is 0. When it is 1, 1 square is 1. So this is my relation. Now let me just draw the arrows. -1 is related to 1. 1 is also related to 1. And 0 is related to 0. Okay, so this is my F. Sometimes we show the function name here in the middle of these arrows, like this, in an arrow diagram. Is it a function? First of all, let's just verify that. What is the condition? No soldier on this side should sit idly. If everyone needs to attack someone, yes, that is happening. -1, 0, 1. Everyone is attacking someone on the other side. And each soldier should attack only one soldier. In other words, from each point here, only one arrow should go out. Yes? From -1, only one arrow is going out. From 0 also, and from 1 also. But note that something has happened here. On this side, 2 is sitting idly and safely because it is not being attacked by anyone. Maybe 1 is such an important target that 1 is being attacked by 2 soldiers. And this one is also of some importance, this target, that this 0 soldier is attacking the 0 soldier on that side. But in this chaos, 2 is left out. So 2 is safe for now. That is possible. See, this is not allowed if you think of a function. I mean, what I am trying to say here is that if I change the directions of all these arrows, say I think of a relation from B to A, which also follows these arrows but now in the opposite direction. That is also a relation, but this time from B to A. That relation won't be a function because both the conditions are failing here. First of all, 2 is sitting idly. 2 should attack someone, right? 2 is not doing that. That is one problem. The other problem is that here, 1 seems to be having some kind of advanced weapon which can attack 2 soldiers on that side at once. That is also not allowed. So that is why that relation fails to be a function. Whereas our relation, which we originally considered, is very well a function, in spite of this thing happening on the other side. This particular observation will be very helpful in class 12, okay, when these things are going to be extended to some other ideas. Specifically, I am talking about inverse functions, but those things we will consider afterwards. Okay, there is so much time for that. The thing that we note here is that whatever things are not allowed on this side, exactly those things are happening on that side, but if you change your perspective. That's not a problem for us now, because f is a function, this f. So I wanted to show this example just to show that although every element has a unique image, the image of -1 is 1, the image of 0 is 0, the image of 1 is 1, but every element need not have a unique pre-image, every element on that side, in the second set. For example, 0 has this pre-image, that is only one pre-image, fine. 1, however, has two pre-images, -1 and 1, whereas 2 doesn't have any pre-image. That is why we write a pre-image. Okay. So these are the things about function. Now that we have understood all the things, let us go to some examples. This is one example, but let's go to the actual examples which are there in the text. These ideas may seem a bit overwhelming if this is the first time you are getting them, but that's the case with just about anything, right? Anything you see for the first time, it becomes overwhelming, but the more time you spend with it, the more you try to think of the ideas, the more practice you do, the easier they get. So let us now see this next example. This is example 10 in the text, but I am not going to follow any such numbering. Let n be the set of all, of course, it is the set of all natural numbers, and let the relation, and let the relation R on n be defined as R equal to the set of all ordered. You see one thing, R on n, you remember what this on means from our study of relations. When we say that a relation is on a set, then it is from the set to itself. So those sets A and B in this case are both equal to n. So this x comma y will be an ordered pair of natural numbers, and the rule linking x and y is y equal to 2x. Say this is our relation. What are the domain, codomain and range of R? Okay, so that is old questions. What are the domain, codomain and range of R? But then we are also being asked, is this relation a function? Is this relation a function? I think I am running out of ink. This is one thing that you have to understand. I mean, this notion of functions. Because anywhere you go in mathematics, you are going to have functions. Without any doubt, this is the single most important notion in maths. There is no debate on this. Sets are also important, but functions are even more important. And things you are going to learn about functions, I mean, right now we are just simply seeing what functions are. But later on, when you go to second year, I mean in class 12, there you will see special types of functions. Already functions themselves are a special type of relations, but then we are going to classify functions themselves into some special types. Those things you are going to need everywhere, no matter where you go in mathematics. And unfortunately outside of mathematics also. Okay, so let's now solve this one. I say unfortunately because many subjects, especially the sciences, use mathematics, and this use sometimes becomes so heavy that they also need to learn a lot of mathematics, which is really difficult for them because maths is not their main object. They are interested in something else, right? But maths takes up a lot of time of them. So they have to work really hard, especially physicists. So what are the domain, codomain and range of R? What is this relation? This relation has the first set in and the second set also in. So codomain of course is just in, that we can say straight away. So let's just say that first. The codomain is in. What is the domain? The domain by definition is the collection or the set of these first elements of all the ordered pairs in R. Now, are you able to put just any natural number in place of x? Yes, because then your y is just twice of x, which is also a natural number. If you take the double of any natural number, say 1, its double is 2. That is also a natural number. For any x in n, 2x is also in n. That is why there is no problem in putting just about anything from n here. And so the domain is also n itself. Since for any, instead of writing x, let me just write n. You can write x here if you want, you can write anything. We have 2n also in n, and hence n comma 2n belongs to R. Because of this, the domain of R is n. And what will be the range? The range is the set of all these y's. The y's need to be what? They should be even natural numbers because they are twice of some natural numbers, each one of them. The range of R is the set of all even natural numbers. If you have a habit of simply writing integers here. Whenever you see even or odd, you have a habit of writing integer after that, then that will be wrong, because integers can be negative as well. So even natural numbers. But the most important question is this: is this relation a function? You cannot draw arrow diagram. I mean, you can draw, but you won't be able to ever finish drawing the arrows, because the sets involved here are infinite. You keep on writing 1, 2, 3, 4. You cannot end this. On that side also you cannot end. So you keep on drawing arrows. That's not how you should look at a relation when you try to see if it is a function. All you need to see is that each element of n needs to have a unique image. Each soldier needs to attack and attack only one soldier from the opponent team. In other words, you recall the alternate formulation of the definition of function, where we said that for a relation to be a function, the domain should be the equal to the first step. That's the case here, right? The domain is n. And each element from the domain should have a unique image. Since each element has the unique image 2n, so R is a function. R is a function. So this is another example of a function. There is another one. This is a little silly. Let me first write it, then I will say why it's a little bit stupid. Examine each of the following relations and state if it is a function or not. The first relation, all of them have been given the name R, but they are all different. 2, 1, 3, 1, 4, 2. Number 2, 2, 2, 2, 4, 3, 3. 3, 3, 4, 4. And then number 3. The third one is a bit big. One, 2, 2, 3, 3, 4, 4, 5, 5, 6, and 6, 7. The reason this example is not exactly correct is that you need, see, it's not enough to just simply write the set R. We also need to say what those sets A and B are. You remember one exercise from the previous section in that community post. We noted that one relation like this was given and it was asked what the domain and range of that relation are. There in the just below the solution, I remarked that although we can determine from such a relation its domain and range very easily, but we cannot say what the codomain is. Here, however, we need to determine if these relations, each one of them is function or not. So if I don't know what the first set A is and what the second set B is, how do I know that all the soldiers in the first set are attacking? I mean, here we have only those soldiers that are attacking. What if someone is sitting idly? How do I know that just from this? That is why it's a little wrong. But maybe the authors thought that all the soldiers are already attacking. Okay. But that needs to be explicitly mentioned, right? So in that sense, this is actually wrong. But let's just go ahead with that assumption that the domain in fact is, I mean, the first set itself is the domain. And in case of this first one, the first set A has these three elements, 2, 3 and 4. So all the soldiers are actually attacking in all these three cases. That's not the problem. But the problem may be in that a soldier may be attacking more than two persons. More than one person at a time. So I am going to write the solution also accordingly. We are assuming that each of the above, or how do I write this? Okay, we can write like this. Each of the above relations has this way also I cannot express this. What a messy situation. See, this is what happens when the book quality is really not good. Instead, let me just start with the first one. We assume that R is a relation from A to B. Yeah, this way it will be easy to express, where A is 2, 3, 4 and this is a subset of B. If we assume this, then each element of A is having at least one image, right? So that part does not cause any problem. Now we have to only see that each element has a unique image. Since each element of A has, are we having unique image? Yes. the image of 2 is 1. We do not see any 2 in here elsewhere as the first element. Do you see, now it's so convenient to in fact say the things. Without the sets A and B, and especially without the set A, how can you even say, how can you fully know that this is a function or not a function? I don't really know who are writing these books, whether they really don't know these things properly or they are careless, I don't know. Has a unique image in B under R. R is a function. R is a function from A to B. B cannot be determined. The only condition is that B needs to contain the range, which is 1, 2, the set of all the second coordinates, the range of the relation. So here R is a function. And note that R is a function regardless of what B is. B may be this set or B may be a larger set having elements other than 1 and 2. In all such cases, your R will be a function. In this case also we are going to make such a similar assumption, which we won't write it here. We won't write means you please write, but I won't write it. So let me assume that that part is there. You understand what I mean. Again, we assume that this R is a relation from A to B, where this time A consists of the elements 2, 3 and 4, and B is a set which contains the elements 2, 3 and 4. Okay, so at least let me just write here A is this set and B contains, or B is a superset of this. But we have already run into a problem here, because 2 has 2 images, 2 and 4. Since 2 from A has the 2 images, two and 4 in B under R. So this R is not a function. R is not a function. It's not a function from A to B. It's a relation, however, from A to B. And finally, we come to number 3, which also has to be started like that. In this case, A will consist of the first components 1, 2, 3, 4, 5 and 6. And 2, 3, 4, 5, 6 and 7, these elements must belong to B, or in other words, the set consisting of them should be a subset of B, and R is supposed to be a relation from A to B. This will be a function since each element of A has a unique image, because you can see 1 has only the image 2, 2 has only the image 3. In fact, in this case there is a pattern also. You just have to add 1 to the first component, and that gives you the second component. So that's why this relation is a function. Since each element of A has a unique image in B under R, R is a function. Next, there is a definition of real valued functions and real functions, but I suddenly remember something. Let me just say that one first. Say you have a function f from A to B. Each element of A needs to have an image, a unique image in B. Now you may of course think of it like that game of shooting, fine, but you may draw another analogy which is really close to what functions really are. You think of a function as a factory or a device in which you give some raw material and it produces some product. A is the warehouse or the godown containing those raw materials. What you do, F is the machine. In the machine, you put your raw material coming from A, and that gives you a finished product B, which then goes to this warehouse, and then from there it may be distributed to the retailers, to the shops, whatever the business wants to do. So the thing is that A is the warehouse consisting of the raw materials which are apt for this kind of production. I mean, if you say want to create cars, right, then you will need many things. So if this is a machine that is producing cars, just hypothetically speaking, okay, then you would need many things. You would need steel, you would need glass, plastic, many things, but you of course will not need flowers, for example. So that's why we need A to be consisting of reasonable objects that can be put in the function, in the machine, to give you a product B. And of course, when you put some things in F, you get only one product at a time, not more than one. Also, you will, because you are going to put some reasonable initial products, not say flowers, or say you throw in a person in the machine. What comes out is the mangled remains of that person. No, that is not allowed. So that's why only reasonable inputs are allowed, and in this sense, the things you put in the function are also called inputs, and whatever comes out is output. For every input, there is exactly one output. Okay, so I just needed to say this. Now let's see this next definition. In this next definition, we are going to concentrate on some special types of functions, mostly which we are going to consider in our study. Have you noticed one thing? The general nature of these sets A and B allow us to actually take anything as objects, as elements in A and B. A and B need not always have numbers. They may have other things also. And there are places in mathematics where we consider functions whose inputs and outputs are not numbers but something else. There are important functions which are needed where the input is a vector, the output is an ordinary number, or maybe the input is an ordinary number, the output is a vector. However, if f is a function from, there is no real need to write from A to B, but I can just simply say like this. If f is a function whose range is the set of real numbers or a subset of R, then such functions are called real valued functions. That is, functions whose values or the outputs they give are real numbers. Then f is said to be a real valued function. Okay, so when we say a real valued function, you have to understand that the outputs are all real numbers. Note that just now I have said that some functions have vector inputs. But if the output is a real number, then such functions are real valued functions. If in addition say you take a real valued function, but now besides that something else is also true. If in addition the domain is also R or a subset of R, then f is called a real function. That means a real valued function is a function whose range, this is of course not the range, this is the codomain. If the range, that is the set of outputs, is a subset of R or is equal to R, then we say that the function is a real valued function. Say this is true, and additionally the domain, which of course is always A, is also either R or a subset of R, then such functions are called real functions. Okay. So we are going to mostly consider real functions in whatever we are going to see next. Now there is one more example. Let's just do this and then we will stop. There are other special examples that come after this that we will do in another video. This one is very easy. It just asks us to find some function values. Define the function f from the set of natural numbers into itself by f of x equal to 2x plus 1. Now this may at once look a little confusing. We are saying that, say define the function like this. This is not looking like a function. Of course, we understand that f is a relation from n to n. But where is the set f? We do not see a set here. Actually, there is no need to write the set every time. The set in this case will be this. such that y is equal to 2x plus 1. Because we have you remember the notation when this happens, when an ordered pair x comma instead of writing x comma y belongs to f, instead of writing this, we write y equal to f of x. Now this y is 2x plus 1, right? And that is why only this has been mentioned. Once you know the relationship between the input and the output, what the output should be for a given input, you automatically know the set. That's why we won't show this set any longer. We will write the relation like this. In fact, this is the relation and this is the function. So the question here is this: find f of x when x is these values 5, 6 and 7. Of course, I am not going to find all of these. I will say find the function value for say 3 of these inputs. The rest I will leave to you. This is how you should write. The value of the function at when the input is 1 or f of 1 is equal to 2 times 1 plus 1, that is 3, and let me calculate f of 5. This is 2 times 5 plus 1, that is 11, and let me calculate f of 7. So this is 50. So that's just it for tonight. After this we have some special types of functions: polynomial functions, rational functions. So we will see what those things are in the next video. And tomorrow, as usual, we have our Galva theory. So that's it. See you tomorrow. Until then, this is me, Lucifer, from a mathematical group. Have a nice day.